Right, our final speaker is Junke, Associate Professor of Civil and Environmental Engineering from the University of Nebraska-Lincoln. And I will go get your slides up if you want to just go ahead and get started.
Yeah, I'm Junke. I'm an associate professor of hydraulics and hydrology. Most of my work is, unlike today's presentation, is fundamental research for water resources engineering. For many years, I do the basic research on hydraulic fluid mechanics. Just the last 3 or 4 years, I switched to hydrology. My purpose is reformulate the fundamental theory of hydrology. Okay, we know a watershed process mainly includes 3 components. One is the rainfall. When we have rainfall, so first we have infiltration. So then we have surface flow. Okay, I built 3 fundamental laws for these 3 components. And the first one is 3 years ago in this conference, I presented the general uni-hydrograph model. That means currently we have the model, watershed model based on uni-hydrograph. That is a graphical empirical. Or even now I only use 3 parameters. A watershed has like a DNA has only 3 parameters. If we know these 3 parameters, we use a model, we could produce the water process in surface water. Okay, that's the first. This paper is widely received in ASE journal read. The second one is infiltration. I overthrow the 100-year classical infiltration theory. Okay, great after all these use Newton's methods, establish a new method that is called general infiltration law. Okay, that can reproduce the widely used the Horton's infiltration equation. That is a special case of my theory, and this theory is very well received in the community. Okay, and Dr. Rain and our scientists trying to nominate that paper for the best paper in whole ESE, the normal medal. Okay, and also a professor in University of Iowa, and he will also try to nominate. This is a revolution for 100 years because we demonstrate, mathematically proved the existing theory, infiltration theory, is wrong. It's a self-contradictory. Okay, so we build a new theory, and the new theory is very, very simple. Very simple. The Horton's infiltration law is a special case for that. Today, we talk the third one. This is about the infiltration and rainfall. And this paper has been accepted by ASE Journal of Hydrological Engineering. And in this paper, what we talk about is, you see, if we see a cloud outside in sky, how do you know? And this cloud will have rain, produce rain, and when it starts to rain, and how long does it last? What is the rainfall distribution over time? Today's presentation is about a rainfall law. Okay. Previously, we said we all about the rainfall distribution is based on empirical previous data. Okay. When we design hydraulic structures, watershed design, we build extreme based on previous data, or we trying to if we try to understand a watershed process, we have rainfall, we have surface flow. We try to build the empirical relationship. But now this one is specific. Now outside we have a cloud. If we use radar, we can measure the particle size distribution. That distribution. We know the macro structures, what is the height of the cloud, what is the thickness. We can immediately predict what is the rainfall process. Okay, that is, how to put on that?
Try that right.
Yes.
Right button. Is it?
Yeah, I put it here. Yeah, what is it?
I don't know if it works with the PDF.
Okay.
Sorry.
Yes, it's fine. So that is So general, okay. We say the problem, okay, this one is, I said, what is the general idea is we need to know what is the rain drop size distribution in a cloud. If we know the distribution, okay, we know, okay, you like the sediment in water, okay, you have a sediment water, you have a size distribution. We know the large sediment will move fast, right? The small sediment will move slow. The rain drop size is exactly similar like this one, except now we have raindrops, droplet in air. Okay, so this one is, once we know this one, we can calculate, predict the height graph model. Okay, so what is it here? What's the straightforward? If we have a rain, we have a cloud in sky, can we now cast its rainfall distribution in the coming time, in the coming 2 hours? Okay, now we have a weather. We say we have a rainfall probability is 20%, 30%. That is based on, okay, is satellite data. Okay, we compare the data to previous data. We know this probably we have 20% rainfall probability, but now we don't need that. Okay, so what the motivation is real-time rainfall height graph are critical for cloud now testing. Okay, the non-testing, that means immediate real-time in 1 or 2 hours. Okay, how can I still see in 1 or 2 hours if this one have a rain, and what is the rainfall distribution? And conventional and EV today's we talk about the AI, machine learning. All these are based on historical data. Okay, we have pictures, we have satellite data. We compare this data with our previous data. So I say that probably have 50%. No, this my method is exact mechanical method. Okay, and why we need this one? Lack of predictive rainfall data has led to tragic flood events. You know, the recent Texas, Central Texas. If we know the cloud, we could immediately calculate how this cloud rainfall distributed. We could save more than 130 people's life. Okay, so what is this? The objective is develop a mechanistic based on mechanics to generate a rainfall height graph from what? From cloud size distribution. Okay, and this model enable real-time flood forecasting using the this one is some physical laws. Okay, so we say what is the method? The idea is we have a cloud, and if we measure, use radar or satellite, measure the droplet size distribution. So then we have droplet descent dynamics, like the sediment move, the sediment settling in water. Okay, so then we can calculate the rainfall height graph. Okay, so this one is previously, this is the first time we predict the rainfall in terms of mechanics based on physical principles. Okay, and what is it? How we made several hypotheses. The cloud exhibit this is based on some mathematics. Okay, it's fractal. That means irregular, and chaotic. So what is the cloud? The cloud doesn't matter how you look at the cloud; they are always similar. In particular, the drop size distribution is very small. That is independent of any large scale or the macro scale. So that is, we do not go that way in detail. Okay. So based on this theory, I developed this model. This what is this one? This one is the particle size distribution. This first one. How does that mean? Like a probability, cumulative probability. And this one actually is our rainfall distribution. Rainfall distribution. Okay, and another is size distribution. Okay, we will derive a rainfall distribution based on this one. So let's first look at how this one agree with the data. These are the droplet science data. Okay, this is the first time in history in this hydrology and meteorology, we have a similarity model. We have one model we predict the drop size distribution from different clouds, from different size, different rainfall intensity. We have this cumulative intensity. Okay? And this solid line, we can predict the classical data, classical very well. Classical data. Of course, we compare to other the gamma or log normal distribution. They're not good. So my model predict this one very well. Okay, and if this is a cumulative particle size distribution, and what is the in terms of probability? Yeah, this is one. So this my model can produce that is based on the fractal theory. Okay, so can predict this data, classical data, very well. Okay, and this data from what you see, and from some rainfall intensity is very small, like a drizzle, and someone is this one is the rainfall intensity is very large. However, we have one equation, we could collapse all these data, in terms of similarity. Okay, so if we have this one particle size distribution, so then we know the height of the cloud. We could calculate how this rainfall distribute over time. So this is the general idea. Okay, first we consider a theme. This one is thin. This cloud is thin. Okay, and we can measure. You use radar. We can measure this height. Okay, if we know the particle size distribution here, so then we know. The larger particle will reach the ground first. That means the rain is stopped. Okay, the smallest, not all these particle size will produce rainfall because some finals, because of air turbulence, never produce that. They always suspended in air. Okay, so this is the story. So the largest, when the largest particle touch the ground, we say the rainfall is a start. Okay, when the smallest usually is 0.5 millimeter, and smallest not the real because less than 0.5 millimeters, those one do not produce rainfall. Okay, that go to this one. So at this point, you know the rainfall stops. Rainfall stops. So this one is distribution. And this distribute, this is a small particle, this is a large particle, and this one is we call it a critical. Less than this minimum particles, and they will always stay in air, do not produce. So produce rainfall is this one. This one first reach the ground, so that we start rainfall. Okay, so this point is the smallest one. And once this one comes, so this one here. We say the rainfall stops. So based on this one, and this one is the settling time from the cloud, settling time, and we could produce this. This one is, or we assume this one is seen, because this is we see all particles start to form together. They're simultaneous. Okay? We have an equation for this one. Once we have this one, so then we consider a thick, if we have a thick, very thick cloud, we can divide them in many small layers. So we can use a superposition to find if we have a thick cloud, we can find what is the rainfall process. Okay, here the persistent. So we got this one is for space. We can divide it in many space, small thin layer. Okay, and if for some for persistent. So if we have air, the cloud from our place, in our case, in Omaha, we know Omaha, why we have rainfall in Omaha? Because from north, we have the cool air. Okay? From south, we have a warm air. Okay? When they meet together. Okay? So in that case, we can probably have a persistent. That means you always have transport clouds from out we have a superposition in terms of time. Okay, and here, because I just talk about the idea, do not talk about the equation. This one is an example in Omaha. Yeah, in Omaha, okay, Omaha from south, from north we have cool air, okay, and in south, this north, this is north. From south we have a warm air, okay, the way the climb there. So the warm will rise. So finally we get this one. And usually, if we know the particle size, raindrop size distribution, this is cumulative. Okay, if we use the radar, we can calculate this part. That is the size distribution. Based on this size distribution, here we consider is two layer. One is 4,000. Okay, the other layer is 10,000, for example. So first, this lower layer will produce this part. The higher layer, okay, produce this part. So if we superpose it, then we get this one. This is the rainfall process. It's a general idea. Okay, and I also produce for thick, Singapore. Okay, for Singapore, and also consistent like a typhoon. What's that? Typhoon rainfall, okay, in Taiwan. All these are, we do not compare them quantitatively. However, all these shapes could produce some experience data, okay? So based on this one, we propose the next generation flood nowcasting. Nowcasting, I say, is immediate, real time, next 1 or 2 hours. Okay, so first we have this radar. Okay, we have this radar. As you see, our satellite, we measure this cloud. This cloud in terms of macro height, thickness, or this one. So then we can calculate with the size distribution. And once we know the size distribution, so then say the rate drops start to descend. Okay, and the descent with this descent, yes, this is the time. Okay, and the larger will be faster. Okay, and small will be large. So based on this one, we can calculate. We call it is rainfall distribution or histogram or rainfall distribution or over time. We get this one. Once we get this one is the rainfall on the ground. Say some will go to infiltration, okay, and infiltration is some problem. So then the surface water we have the surface water we use my general unit hydrograph model. So for the general infiltration law, yes, for infiltration we can also, once we have infiltration, the water into soil, we can also use my general unit hydrograph model. In part we call it interflow subsurface flow. Okay, so then this is groundwater. There's 3 water added together, we get a stream. Okay, this is before rainfall. Okay, the rainfall has not started. We already calculate this one. Based on this one, okay, we can have a flood warning on our casting. If we know this, we use this technology in our central Texas, July 4th. Yeah, we can save the lives, save lives. So this one is the journal. This paper is a long paper in ASE journal, just accepted recently. Accepted recently. And people say that this one is a new idea for nowcasting. And all previous is statistical or even AI is based on statistical, but this one is specific for specific clouds. Okay, and is based on mechanics, based on physics. Okay, however, there are still a lot of work need to do. The challenge is in measuring cloud macrostructure. Yes, we said, how do you measure the clouds accurately? That's because it's irregular. Okay, that's one problem. The other one is the assumption is may oversimplify the real dynamics. Okay, we do not consider the interaction between particles during their rainfall. Okay, and it's validated with model remote sensing data. The current data is based on old one, and the other one we lack data, simultaneous data from and the rainfall. We do not have this data. Okay, so yeah, I know that some of you have the data. If possible, we can find some collaboration. And recently, a company in UK, as an insurance company, asked me to talk about this one. They said they are insurance company. They are interested in this technology, trying to put this one. I don't know. I have not do that. They just sent me email yesterday if I have a lecture for their company. So the conclusion is this research introduced a physics-based real-time rainfall modeling framework. It still has a lot of work to do for practice. Here we have a general power law distribution. Outperforms traditional this drop size, drop leader size distribution model. This is usually traditionally in meteorology and hydrology, the people use a gamma function, also use a log normal distribution. However, those distributions, they cannot clamp all data into one curve. Okay? This research offered transformative potential for flood early warning system. That means in 1 or 2 hours before the rain. Okay, that is yes. Yes. Okay, yes.
It's two questions. One is about the droplet interactions, because in my mind it's gonna break, it's going down. Then it start like that big, and either way it's gonna break in different.
Oh, yes, yeah, that's a good question.
And again, it's gonna get together.
Yes.
The other question is the wind. The wind can mix this droplet.
Yes, great question. But because this one is based on statistics, when we talk about the science distribution, is a statistical already considered those mixing. Yeah.
Maybe we could put a parameter to parameterize the. voltage.
Yeah. But at this moment, I say that we simplify the process. We didn't consider the interaction during the interaction. However, if it's a single, just the one cloud, that seldom occurs. Why? Because the larger one move faster, the small one move less, so they do not.
Okay, that's okay, but my question is it's large here, but gonna break, it can break, and the large can be the smaller.
Okay, oh, you say the cloud, yes, right.
The drop.
At this moment, yes, we cannot achieve that. At this moment, is we consider very simple one. We have a cloud. Okay, if you have a cloud moving, that's easy to calculate. Like just you have an airplane, you drop the bomb. Yeah, it's exactly the same. Yeah. So the most important is the particle size distribution. If we find a similarity law, we can collapse all from different clouds and with different ripple, we can clamp them together into one single curve. Once we know that one, we could predict the rainfall distribution.